Hello, welcome everyone. My name is Mark Brown, and welcome to our session, Data Modeling and Partitioning in Cosmos DB for achieving infinite scale in your databases. My name is Mark Brown. I'm a program manager on the Cosmos DB team. You can find me on Twitter most times. I'm at Mark J. Brown. Feel free to reach out if you need. And follow our Twitter handle as well as at AzureCosmosDB.com. Okay, let me move a slide here. Come on. Okay. For today's session over the next hour, we're going to help you get familiar with core concepts for data modeling, best practices, and we're going to apply these to a quasi-real-world scenario, and I'll show you that. And then hopefully, for most of you who I'm guessing in the room today are new to Cosmos DB and are familiar with relational databases and how to model for those and make them run efficiently. Hopefully this session will help you understand how to jump from that relational world to a NoSQL world and learning how to design and model for a database like Cosmos DB. So what is Cosmos DB? Well, officially, it's Microsoft's NoSQL database on Azure. And when we say NoSQL, what we mean is that Cosmos DB is both non-relational and also horizontally scalable. So let me dive into the horizontal scale aspects of Cosmos DB. Unless your workload is really small with just a little bit of data and request, you're likely going to be storing your data stored on a number of different servers or what we call partitions within something we call a container. Now in Cosmos, we abstract all this away, but under the hood, you're reading and writing data from a cluster of servers. And this is better known as scale out. And it's how we achieve this horizontal scalability. And it has some benefits, enables practically unlimited storage, theoretically unlimited or infinite. So when you need more servers, we just simply keep adding more to your account. Also, because each of these servers has its own CPU and network card and memory and I/O, it also provides unlimited throughput to handle the request when you need it for your database. So Cosmos DB is also non-relational. Now, when you're working with a relational database, you have the ability to define relational constraints like joins and triggers and all these other different constraints, foreign keys, primary keys, all these things. And this lets you do things like do join operations across these different entity types. But in a database like Cosmos DB, we don't implement any of these relational constraints. Now, you may be asking why? Well, because Cosmos is horizontally scalable, and because your data is likely going to be spread across multiple servers. Could be tens or hundreds of servers, depending on your throughput and your storage needs. Now, I don't want to suggest that it's not technically possible to enforce relational constraints and put locks on data across a cluster of servers, but doing so could have enormous performance impacts and also can impact the availability of your database if, say, one of those servers goes down. And because Cosmos is designed to provide predictable performance above all else, we don't really provide a way to declare these types of relational constraints and do this across a cluster of servers. So you may be asking, well, is Cosmos even suitable for relational workloads? And the answer is yes, definitely. In fact, most workloads on Cosmos are relational. You just need to learn the different techniques to implement these relationships between your entities. Now, this approach is very different than designing a data model for a relational database. And for those of you that are new to this type of database, you should not follow your intuitions here. Best practices in the relational world don't translate well to this type of database and may even be an anti-pattern for us. Okay, so let's put this into practice. I'm going to spend the rest of the session and I'm going to take a relational database that I think anyone who's used SQL Server, and hopefully that's most of you in this room, should be familiar with, and that's the AdventureWorks 2017 database. Well, actually, we're just going to take a subset of it. Now, these tables represent kind of a canonical e-commerce workload. We've got our customer tables, so I've got a customer here, and then I've got customer address, and then, of course, I've got a customer password table in here, and I've got relationships defined between those things. We've also got product tables, so I've got my product table here. We have a product category table with a one-to-many relationship, and then we have a product tag, and then a many-to-many relationship to a product tags table within there. So I've got a cross-product of products and tags stored within that table. And then finally, we've got our sales order. So I've got sales order here, and then sales order detail. Now, with a non-relational document database like Cosmos DB, there isn't much we can do with this as is. You would never use these tables as is when you're trying to perform your operations on it, because the cost of accessing and managing this data would, in fact, be prohibitive. Another thing I want to point out, too, is that in a relational database, the relationships between the data is very important to modeling the database. For a database like Cosmos, this is actually only part of the story here. What's most important when designing a data model for a NoSQL database like Cosmos is the access patterns for your data. And as I go through this talk and we remodel this data from relational database, from a SQL database to a NoSQL database, we're going to talk about these access patterns and how it impacts the choices we're going to make when we're modeling our data. Okay, so let's talk about these access patterns for our app. Our real e-commerce platform would likely have a lot more different types of operations they would need to do. But for our purposes here, we can kind of boil it down to these operations here. So for customers, I want to create a customer, edit a customer, and then, of course, I want to retrieve that customer, particularly when they log in. I need to create and edit product categories. I need to list all my categories. I need to create and edit product tags and then list those. Create and edit products. And then I want to list all products from a category. And I also want to include the name of that category as well as the name of the tags in there. And then finally, I want to create a sales order. I need to list all sales orders for a customer. That's a very frequent operation. And then I've got another special query in here. I'm going to query top 10 customers by the number of sales orders. Let's say I've got like a loyalty program and I need a way to identify my best customers so I can send them a special gift every month, maybe a gift card or something like that. Okay, so those are kind of the main operations that our e-commerce system is going to do here. So let's get started. And we're going to remodel this database from a relational model to a NoSQL model in Cosmos DB. And let's start with our customer entity here. So we've got 3 tables here. First thing I need to do is Cosmos is a JSON database store. So we need to translate what we've got as tables into corresponding JSON documents within Cosmos DB. Now, we could keep these in separate containers within Cosmos DB, right? The container is kind of the logical wrapper around your data, if you will. For us, everything is a partition, right? That's the server it sits on. So the logical grouping of those things, and you could kind of think of it as a table, but that's not quite the right way of thinking about it. But let's talk about containers here. Now, we could store these as in separate containers, but let's look at the operations we need to support here. We've got to create a customer, we need to edit a customer, and we need to retrieve a customer. Now, given that Cosmos stores data as JSON, another approach we could take here is to actually embed the address and the password data into our customer table here, or into our customer container. Now, when I create a new customer, I only need to insert data into a single container. It's all in one place. Reading data is also easier because I only need to read from a single container as well. So let me go into the portal, and I want to show you kind of the benefits you have with that. So let me do my first little demo here. And here I've got, well, let me show you here. I've got, this is my Cosmic Works. And by the way, I'll show you a link to where you can get all this stuff if you want to see it. But what I've got here is a Cosmos DB account, and I've got 4 versions of this database in here. And this is the evolution of this data model as I go from a very naive model here. So I've got one container per entity. So each thing that was a table in, say, SQL is now a container here. And then as I go through, you will see that I'm going to evolve this data model. So here you can see I've actually got fewer containers in here because I'm evolving this model and I'm embedding data. So let's see, what is the cost going to be and how many operations do I have to do if I use a very naive, like a relational model for databases here. So this is going to query my customer container here. All right, and let's run this one. And here's my customer here, Destiny Peterson. And let's take a look. I can get the cost of that query by clicking on Query Stats here in the portal. And you can see about 3 RUs per second for the cost of that. That's a request unit per second. Now let's get the customer address. I need to get my customer address so we know where to ship stuff, or the customer can select their address to ship it. And we'll run that query here. And Where are you? Oh, there you are. Okay, so I've got my address here, and let's get our query stats. A little over 11 are used, so a little more expensive, but there's probably a lot more addresses than there are customers in this database. Okay, and last, let's query the customer password. I need the password so that when they log in, I can get their password and verify that they're the right person there. So here I've got the password here for them, and let's get that. And that's about 3 RU. So I've got about 3, 6, and 11. So that's about 17 RU, maybe a little less on that. And that's just one request or one operation, if you will, which is I need to retrieve that customer. Okay, so I've got 3 queries, 3 different requests, and it's costing me 17 RU. Now let's try when I embed this data. So this is from my version 2 of my database, and I'm going to run this one here. And here I've got all of my customer data. So here's the customer email name, email address, phone number. Here's their address. And then here's their password. So what is the cost of that? Well, it's just that 2.83 RU on there. So I've made an order of magnitude better performance, at least cost for the database. But the other thing as well is that I've done this in a single request. So the latency is going to be better and less CPU usage on my client as well. Okay, so better performance when I embed data like that. And this is the nice thing about a database like Cosmos DB. Operations are faster, and they're also less expensive to execute because I've embedded this data inside a single container. Okay, so at this point, people often ask, well, when would you embed data versus, say, reference that are stored as a different row? And there's actually some good rules of thumb around this. In fact, you generally want to embed data when there's a one-to-one relationship for the data, for the entities themselves. And in this case, customer password, there's a one-to-one relationship. So that makes it a good candidate. Also, another scenario is a one-to-few relationship. Now, you may be asking, well, what is one-to-few? I know one-to-many, but I've never heard of that. One-to-few is a one-to-many relationship, but it's a bounded relationship. It's not open-ended. You could think of customer address as a one-to-few relationship. Typically, customers are going to have a handful of addresses they want to ship to, right? They've got themselves, maybe their mom, their dad, or their brother, or their sister, or other relatives. They maybe have, I don't know, 5, 6, 10. It's a bounded set. Something that's unbounded likely would be maybe comments on a post for a blog or something, right? I mean, they may be bounded in some respect, but let's just say if your blog post got picked up on Slashdot or something, or on I don't know, just went viral, and you got thousands of posts. At that point, you're largely kind of unbounded at that point. And then the last scenario is if the entities are either queried or updated together. So that's another scenario because you're going to be able to do that in a single request versus multiple requests. Like with our customer data here, that data is always pretty much queried at the same time or requested at the same time. So that's a good relationship, or that's a good scenario for putting that together. Now, you want to reference data when the items are in a one-to-many relationship, right? So that unbounded relationship is what we're talking about. Also, many-to-many relationships, you want to reference that data. There's also another thing you can do with it as well, and we'll talk about that a little bit later in our talk. And then, particularly when related items are either queried or updated independently of each other, this is also an area where you should look at separating that data or storing it as different documents within your container. Keep in mind that as documents get larger within Cosmos DB, the cost of doing operations on it can grow quite dramatically. It's not linear, if you will, so it can kind of grow like a hockey stick. So if you have a pattern where you have kind of asymmetric updates happening to, say, a small number of properties. So I've got a small number of properties, but I update those very, very frequently. And then I have another set of properties, maybe a larger set, that I don't update as frequently. That's a good scenario for where you would want to, say, shred that document, where you have your small number of properties that are updated quite frequently. So there's high concurrency with operations on there. And then another document that has largely static data. And then if you want to bring it together, you just query for it so that it brings back both documents, and then you can deserialize that into your classes and then use that within your application. That's a better, more efficient design for a database like Cosmos, particularly if they're not used at the same time. You really just want to be very efficient with the requests, the payloads, and just be smart about how you're accessing that data. And again, it comes down really to the access patterns for your data. Okay, so we have our one-to-one and one-to-few relationships between our entities here. And because we retrieve all this data at one time, it makes sense to embed everything inside a single JSON document. Now that we've defined our first entity, we want to store this in our customer container. That's what we'll call it. We'll call it customer. Now, when creating a new container in Cosmos DB, you have to define a partition key for that data. And you may be asking, well, what is a partition key? Well, remember earlier when I referred to Cosmos DB as an abstraction over these different, like a cluster of physical servers in here. Now, when storing documents in a Cosmos DB container, these documents end up being dispatched to these different physical servers. So the question is, well, how do I decide which document goes to this server and which document goes to that server? Now, technically, we don't really assign documents to servers here. Instead, what we do is these documents are being written to something we call a logical partition. And it's these logical partitions that sit or reside on these different physical servers or physical partitions. And so from a user's perspective, you don't really need to care about the physical servers. We try to abstract that away from you so you don't have to think about that sort of thing. It's just you need to know that this data is going to get to these different logical partitions. Okay, so how do I decide how these data gets stored on a logical partition? What we have is the partition key. And so when you define or create a new container in Cosmos DB, you assign this a property that's within each one of your documents, and it decides which logical partition your data is going to go to. Think of it as an address to kind of route your data, right? Now, using this example of a container here, we've got one that's partitioned by username. So when we insert data with username of, say, Andrew, it's going to go to that partition, or with Deborah or Tim, it'll go to the corresponding partition that equals that user's name. Okay, so there's some constraints you need to keep an eye on when modeling your data for Cosmos DB. Each document has a maximum size of 2 megabytes. Now, remember before when I said, or when I was talking about when to embed versus when to reference, one reason why you want to avoid these kind of unbounded arrays or these unbounded one-to-many relationships is because your documents can't get any larger than 2 megabytes. It's also not efficient, like I said before, when you have large documents and you're only updating a small portion of them, right? The cost of doing so can get prohibitive over time, and it can increase the latency when you're taking and moving a large chunk of data across the wire, because every time you do an update, you're essentially replacing the entire document. Another thing to keep in mind, too, is that each logical partition has a maximum size of 20 gigabytes. So you can't have more than 20 gigabytes for, say, username equals, say, Andrew or Deborah or Tim in there. Okay. Well, when working with data, we want to strive to achieve an even distribution of data across these different logical partitions. So if one partition gets a lot more data stored on it than the others, this is what we call a hot partition. And it's actually something you very much really want to avoid. Same goes for the request as well. If most or all of your requests hit that same logical partition, this is going to be a bottleneck that's going to drastically limit the overall scalability of your model. Keep in mind that as you provision or add more storage and you add more physical partitions behind this thing, you get additional CPU. But you can't like group that or put that CPU all in a single logical partition. It has to be evenly spread, right? And so if you've got additional physical partitions due to more logical partitions in here or more data, or you would provision additional throughput that provisions more physical partitions behind there, you have to, the objective here is to make sure that you're using all of that available throughput that you're getting. Otherwise, what you get is you're going to get bottlenecks where, say, your requests are all still going to that same logical partition, but your other partitions are just sitting idle, not doing anything. You're paying for that throughput, right? You're paying for those physical partitions. It's like a VM in that sense, right? So why would you provision a massive VM and play solitaire on it or not use it for much? It doesn't make sense, right? Economically or in any case. It's the same thing for Cosmos. It's a provisioned environment. You provision these resources as throughput or RUs per second, and then behind the scenes, we provision all of these physical resources in the terms of these physical partitions or physical servers that are there to handle requests for that data and store your data in there. So this is very important that the thing you want to achieve here is this even distribution of storage and even distribution of throughput or requests that are accessing the data on each of these different logical partitions. So partition key plays an important role in both the performance and scalability. In fact, it's absolutely critical in terms of that. So let's take an example here where I've got my partition or my container that's partitioned by username, and I'm going to use this SQL query, select star from C, where C.username equals Mark. Now, you'll notice that this filter or this where condition uses my partition key. And this is a good thing because my query knows exactly where to send, or my Cosmos knows exactly where to send that query to go get that data. So this is always going to perform rather well because it's going to hit that one physical partition or server. Now, let's try something else. So let's say I filter by like favorite color here. We would have no idea where these results are. So in this case, Cosmos DB is going to do what we call a fan out. And it's going to hit every logical partition and thus every physical partition underlying this. And this is what we call also a cross-partition query, and meaning it's going to hit every one of these physical partitions. Now, this query will work, but it's going to have an impact on latency because it has to go and hit all of these different servers. And it's also going to have an impact on cost because this is going to be a rather expensive query to be able to run. Now, with small containers or small workloads or databases where you don't have much data, the performance impact here is not that bad. In fact, this is kind of one of the insidious things about a scale-out database like Cosmos is if you test something like this and try to benchmark it with a low amount of data, you're not going to see really significant performance issues with it. This is something that you don't really notice that you've got a problem until you get into, say, a larger, more scaled-out environment or into production. I see this quite often where developers will go and they'll build in the design, they'll test, and everything's looking good. And then they go and put it in production, start scaling it up, and then they realize they've got huge problems with performance. This is something you really need to test and understand, not just the access patterns, but also the frequency of them as well, so that you can understand how is your data going to grow over time, how are the requests going to grow as you get additional load on this thing, so that you can make sure that you're designed for scale in the future. Okay, let's keep going. So with all that knowledge now about partitioning, how do we choose what's the right partition key for our container here? Well, again, we're going to look to the access patterns, right, and the operations we're going to do. Now, I said we're going to create a customer and we're going to edit a customer. Now, those aren't operations we're going to do very frequently, right? You're only going to, well, obviously create a customer once for every customer you've got, and then frequently or infrequently would update. The thing that they're going to do is you're going to retrieve a customer. That's going to be your high concurrency operation there. And we're going to retrieve them most commonly by ID within there. So this makes a good partition key for our container. Oh, that slide. Okay. Now, one thing I want to point out is that when using the ID as the partition key for the container, we end up with as many logical partitions as there are documents in the container, with each logical partition containing only a single document. And most people, come and ask me, like, is that a problem? And frankly, the answer is no. It's actually okay. Logical partitions are a virtual concept. You don't have to worry about that. We will co-locate these on the physical partitions behind there, and then move them around as we need to as they kind of grow in size. And there's no upper limit to how many logical partitions you can have in a container. In fact, when you partition by ID within a database like Cosmos DB, you functionally have like a key value store, like a Redis almost within there. So it's not a problem at all. Okay, so let's do a demo. I showed you how to query before with the portal. Let's show you the SDK as well in here. All right, so there you go and pull up. Where are we? Yep, here we go. All right, that's the portal. Now, what I've got is I've got a Visual Studio app here, and I'll show you the code for this. And actually, I'll show you a link how to download all this if you want to. And we're going to run a couple of different operations here. So I'm going to query a customer here. So here's my function to query a customer. I'm going to get an instance to my database here. That's database v2. So this is my now embedded, newly JSON friendly customer data all modeled up in here. And then I've got my customer ID. This is the same customer ID I used before. I'm going to define my query, select star from C, where C.ID equals that ID. Because I want to use my partition key as my filter, right, as my where clause here. And then here's the code to define my query here. I've got my item query iterator, pass in my SQL text there, and then I'm defining a parameter at customer ID. And then I'm going to pass in my partition key, which is also my customer ID. Now, you don't have to do this when you're running queries in Cosmos DB, but this is a good best practice because it better provides kind of more self-documenting code. So I know what the partition key is for my container here. It also just slightly reduces the overhead so that the query engine doesn't have to go and figure out, okay, what's the partition key here that I'm going to use. And then I'm going to write out something here and then loop through, although I'm just getting a single customer, called renext async, and then I'll loop through that customer in my response object and then print it out. I'm also going to show you the request charge that comes out of the response object here. There's lots of good stuff that comes out of the response object in our operations here. I won't go into it in here, but the one I care about most is the request charge because I want to measure the performance here. So let's run my query. This is operation A, query for a single customer. That's taking a second. I haven't warmed this up, so that's just making its first connection. So the latency here is not normal. In fact, here, let's run it again. I'll show you. There you go. It's pretty fast. So there's my customer, same customer, Destiny Peterson as before. Their email address, phone number, create date, address in here, and their password. And you can see here's the same cost request charge, 2.83 RU in there. So that's querying a customer in there. Now, one thing I want to point out is we know the partition key for our customer, and also we're getting just a single. We have the partition key and the ID here as well because it's the same thing. We're also just getting a single item, a single document, row of data, if you will. And when we're doing that, we can use another operation in Cosmos, which is called a point read. Now, let me show you how to do that. So I'm going to get the same database container here, same customer ID, and I'm going to use a different operation here called read item async. And I'm going to pass in two things. I'm going to pass in the ID for the customer, and I'm going to pass in the partition key for the customer. Both of these are required to call that data. And then I'm going to print out my response here and then print the request charge for that. So let me show you that operation here. That's B. Now, I don't know if you noticed, but that came back quite a bit faster than the other one. And the other thing I want you to notice is look at the request charge. It's only a single RU. And what I want to point out here is that when you know the ID and the partition key and you're just looking up a single item of data, especially if it's a high concurrency operation, use a point read, right? The nice thing about these is they're less expensive because they don't go through our query engine. They're faster because they don't go through our query engine. A point read using direct mode for our SDK v3, which is the default, goes directly to our backend data store. The partition key will tell it where's the physical server, right? Because we have a mapping of logical partition key ranges. It's a hash to what physical server it sits on, and that sits inside the SDK when you initially connect to the container. And so when I pass in that partition key, it says where is this data physically located? We route the request directly to that physical server, that physical partition, and then the ID is used to do the index, right? The index seek to find that row of data, that document, and then retrieve it back immediately. So always use these. They're much, much faster, especially for high concurrency reads where you're pulling back just a single row of data. Okay, let's go back to slides. Okay, there's my coffee here. Probably cold by now. All right. All right, next, let's look at product tables here. First up is my product category table. We're going to do the same thing we did earlier, which is translating this entity into a JSON document. And we're going to store that in a container, and we'll call that, unsurprisingly, product category. Next, we need to figure out the partition key for this container here. What are we going to use? And again, we're going to look at the request that we need to support in app. And here, we need to create a product category. We need to edit a product category. And we also need to list all product categories. So this is the query that we would use to get all of those out of there. Now, I want to point out when you're looking at the operations, it's important to know the volume of these operations as well. For instance, we aren't creating or editing product categories very often, but we are going to list them quite frequently. There is another issue here we have as well, which is there's no filter or where on this query. So how do we make this a single partition query? Because for high concurrency operations, we want to try to at least achieve that. And again, we'll look at the, here we need to, what's going on with my slide? Hold on, sorry. Okay, so the answer here is I'm going to use a little trick we're going to apply here, and we're going to create a new property, and we're going to give it a constant value in our document. So here I've created this new property called type, and I've given it a constant value called category within each document. Now, a couple things I want to point out here is, one, there's not much data in product category for this thing. So in fact, I don't need to use this type of technique to create a single partition query for this thing. I could just leave this in its own container and just call select star from C and just get back all the categories. There's only, I think, about 37 categories in AdventureWorks. So it's not for performance that I'm doing this. I actually have another reason why I'm creating or modeling my data this way. And I'm going to show you a little bit later in my talk, because this is actually going to make a lot of sense. And I know for most of you, it probably looks pretty weird here. So let me do, I'll do a little demo here, and I'll show you the queries for that here. So we're going to query product by category ID here. So let me show you this function here. Get a sorry, I want to list all product categories. There we go. So getting my container product category, select star from C, where C.type equals category. Here's my query definition here. My partition key is going to be, the value for that is going to be category, because I'm just using that constant value. And then I'm going to loop all through these here and show you my request charge. So let's list all product categories here. And here you can see, got them all back. There's a bunch of them in here. I think it's 37 total. And my request charge is 4.04. And honestly, if I just did this as a select star from C with no filter, it's going to be pretty much the same cost here because, like I said, this container is very, very small. Okay, let's go back. All right, next, we're going to look at product tags here. So I'm going to apply the same technique I did here. I'm going to put this into a JSON document, and I'm going to put it in its own container called product tag. And turns out I have the same exact access patterns here. So I'm just going to apply that same strategy here that I did with product category. And I'm going to give it a property called type, and I'm going to give it a value of tag. So that's going to have the same value for each product tag in the product tag container there. All right, next let's look at products. First, I want to translate to the JSON schema. Next, I want to look at my relationship between product tags and tables. So our product table has this many-to-many relationship with tags. And I need to access the product tags in my application, meaning that when I display a product, I need the tags to appear for that as well. I may also want to be able to query for a tag at some point as well. Now, I could do this in one of two ways in here. I could store my product info in my product tags table, or I could materialize the tags in my product table, embed them. Now, there's much fewer tags for product than product for tags, so it makes more sense actually to embed this in my product table and do that as an array. Remember, too, there's a one-to-few relationship between products and tags. So this makes it actually a good candidate for embedding in our workload here. Next, we're going to store our product data in a product container. We'll call that product. And now let's figure out a good partition key. So again, we'll look at the operations we want to support here and decide how we're going to do it. So of course, we need to create and edit a product. But the interesting operation here is we need to query for products. And we're going to do that by category in this scenario here, because this may be, or at least we think this is how we're going to search for products. So we want to list all products that match a specific category. So the corresponding query here is select star from C, where C category ID equals, say, category A. And this will return all the products for that category. So in order to make this a single partition query, then we would need to have all products in the same category sit in that same logical partition. So category ID is what we're going to use as our partition key here, as it allows us to retrieve all of our products in a category very efficiently. Now, another problem I've got is that every time I query for products using my category, I get the category ID and then also a bunch of tag IDs that come back. Because remember, this is what our table looked like before, right? Where are you? Right, I got category ID in here, and then I just got my tag IDs that I've embedded in here. But what I need to show, I keep going here, is I want to show the category name for the products in there, right? I need to show that that's the design for the app, is to have that on there. Also, the tag IDs don't make any sense if I display those on a page. I want to show the name of those tags within there. So how am I going to do this? Well, first I need to run my first query to get all the products for that category. And then I need to go and issue a second query to my product category container to get all those back. And then because I have a bunch of product IDs or tag IDs that come back for each product, I have to go and run successive queries for each product that comes back and go and get all of the tag names for each of those tag IDs. Now, this could work, but it's not very scalable. And you may be asking, well, hey, why not just join this stuff, right? Well, again, remember, Cosmos DB is a non-relational data store. We don't support joins across containers. Data that's modeled for this type of data store is optimized such that it can be served in a single request. And that's the objective that you want to apply here. So to our products table, then, what we're going to do is we're going to add some additional properties. We're going to add category name here. We're going to embed that in the table here. And then for each of the tags in the tag array there, we're also going to embed the name for those tags as well. And so by doing this now, we can make sure that we can retrieve all the products for the category and get all the data we need and do that in just one request. Okay, so let's query a product here by category name and get all the tag names back. Whoops, sorry. All right, let me go back, sorry. Okay. All right, so we're going to run this function here, query products by category ID. And here I've got my database reference. Here's my product container here. And here's my category name. So it's called components, headsets. And here's the category ID that I'm going to use. And here's my query, select star from C, where C.category ID equals @category ID. Again, this should be familiar. Here's my query definition, my parameter that I'm passing in, and my partition key as well, right? Okay, and then I'm just going to loop through those and then show all the products for that category. So let's run this one here. This is option D, query product by category ID. And you can see I've got one product here, 2, 3 products, and I've got all of the data I need for them. I have the category name, the SKU, the name, description, price, my array of tags with the ID and the name of the tag in there for each of the products. So I've got 3 products here, and then the total cost of this is 2.91 RU. So that's a good and efficient query for our database here. Okay, all right, let's go back to slides. Okay, so now we've created our new product. Well, what we need to do is we need to populate these additional properties, right? So what if we rename a product category or name a tag, right? So we've got a problem here in that we've materialized that name and for the category and the tags in our product container, right? By denormalizing this stuff and embedding it within there. So the problem here is, what if I rename one of those things, right? How do I manage referential integrity between these containers? Well, as it turns out, Cosmos has a really good way of being able to handle that, and it's called change feed. Change feed is an API that lives within every Cosmos DB container. In fact, it actually lives within every physical partition within a container, but frankly, you don't need to know that. It's exposed through the container object. So whenever data is written to Cosmos DB, such as an insert or an update in this case, change feed can stream these changes to an API, to a delegate specifically, that you can listen to and then use that event to respond to the data that was changed. So in our case, we want to listen changes that occurred to our product category container, as well as our product tag container. And then every time that data is updated, we want to propagate that change to the product container accordingly. Okay, so in this demo, this one's fun. I'm going to show you how to use change feed to do this. So first, I'm going to query the product container for a specific category, and then we'll count how many products we have in that category. I'm then going to update the category's name within the product category container, and then I'll show you how change feed handles those changes and then propagates that to the product container. Okay, let's go back to code. Okay, so we're going to query products for category. We've already shown you that one here. I've got, I haven't shown you this one. So this is what we're going to run. We're going to run this one first. This is query products for category. And the category name I'm going to get here is accessories, tires, and tubes. Okay, and then we're going to do a count on that to see how many products we have within that category. Next, I'm going to update the product category here. So I've got my product category container. Here's my category name. And then I'm going to make a very small change here. I'm just going to change the word and I'm going to replace it with an ampersand instead, okay? And then I'm going to call this, so here's, I'm creating a new product category object here. And then here you can see I'm changing the name of that there. And then I'm going to call this function replace item async. And that takes three things. It takes a partition key, it takes an ID, and then it takes the item itself. And that's the new product, updated product category that I'm passed here. Okay. Next, I want to show you change feed. So it's very simple, actually, and I've only got two things in here. I've got a main function, so my entry function in here, and it's got a reference to a thing called a lease container. Now, lease container is functionally kind of like a checkpoint kind of container. So it keeps track of the last time you picked up any changes from there to whatever's not changed in there. So how change feed works is that it will pull that lease container like every second and say, hey, is there any new changes since the last time I was here? And if there are, it gives them back to you. And the way that shows up is that it shows up in this delegate here, input, and it comes back as an IEnumerable or iRead-only collection. And you can deserialize that into some type if you know what it is in here. In this case, we're going to deserialize that as product category. Next, I'm going to create a new list of tasks in here that I'm going to use to dispatch the changes that come back. And then I'm going to iterate through each of the items that come back in this iRead-only collection. And I'm going to pull out the category ID and the category name because I'm listening to that container. And then I'm going to do something with this data that comes in. And in this case, I'm going to call update product category name. And I'm going to pass in the category ID and the new name that comes in. And then I'm going to call, as I go and I iterate and I add those all to the task list, I'm just going to call when all on that and then dispatch all those to go and run. Now let's look at update product category name here. So this is the function I'm going to call. First thing I need to do is I need to query for all products with that category. So that's going to, here's my SQL statement here. And then this is going against the product container. So I'm going to have, I have two references at the top here, you'll see. I've got my product category container reference that I'm listening to, and my product container. This is the container I'm going to actually make the change to in here. So this is so I'll keep this reference. I've got a query here to get back all the products for that category. And I'm going to iterate through each of those here, right? And as I iterate through each of those, I come back in the response. I'm going to do a couple of things. I'm going to make a count here. So I'm just going to increment this to see how many products we updated. I'm then going to change the name of the category right here. So product.category name equals my new category name that I'm passed into this function. And then for each product that I get back in my response, I'm going to call replace item async on the product itself and update it with the new product category name. All right, so let's run it and see how this all goes. So I've got my main app up here, and I'm going to run this, and I have change feed down here just running, and it's listening. So I want you to keep an eye at the bottom left of your screen as I go and I run this. So let's run this update product category name. So we're going to first print out the number of those products in that category, and I've got 11 accessories, tires, and tubes. Now let's run this. So we're going to replace the update. Now look at the bottom left here. Change feed, one change received, and it's updated all 11 of those products in my product container. Okay, that's basically happened quite fast. Now let's print out that category name so you can see still got the same 11 products, and their new category name is accessories, tires, ampersand, tubes, and we'll change it back. Right, this doesn't like our name change there, and you can see there it's picked it up again. and updated it back to the original name in there. Okay, let's go back to, oops, let's go back to slides. Okay, we're on to our last set of entities here, and that's the sales orders within here. So same process as before. We're going to create JSON documents for each of our entities in here. And obviously, this is another good candidate for embedding because it's a one-to-few relationship. You don't typically have sales orders or e-commerce sites where you have an unlimited or unbounded number of items in your shopping cart, unless you have some kind of problem there. So we're going to embed this here. And then next, we're going to store it in its own container, and we'll call that sales order. So again, let's look at the operations here, and we're going to decide. We need to pick a partition key for what we're going to do. So we need to create a sales order, and then we also need to list all sales orders for our customers. And when we do that, we want to list them by customer ID. So this makes, I think, a good partition key here because we're going to create them by customer ID. Obviously, a customer owns the sales in there, right? It's their sales. And then we're going to do a query, somewhat high concurrency on listing those. Then it makes sense here to do that. And so every single logical partition is going to include all the sales for that customer within there. So we'll make customer ID our partition key here. Now, before we go any further, let's take a step back. When we've looked at the containers we've defined so far, it's interesting to note that we already have another container that's partitioned by customer ID, and that's the customer container. So could we store customers and sales orders in the same container? Well, absolutely yes. In fact, not only is this technically possible, it's actually a best practice for a NoSQL database. Cosmos is schema agnostic, so this is something that's actually totally supported. And it's frankly quite suitable when the data share the same access patterns and the same partition key. Remember, these access patterns really, really matter. It helps really define how you want to store this data and then as well as partition it. So instead of storing customers and sales orders in different containers, we're going to store them in the same container, and we'll call that the customer container here. And I'm also going to change the partition key from ID to customer ID. And then I also need to add, where you are, the customer ID is a property to my customer document as well. Next, I need to be able to distinguish between sales orders and customers because I'm mixing entities within the same container now. So I'm going to add an additional type property here, and I'm going to call that sales order as a constant value for each of the sales orders in there. And then I've got one for customer. This way I can query for these things separately if I want within here. Okay, so now what we've got is within each logical partition of customer ID, I'm going to have exactly one customer document and then all of that customer's sales orders within here. So now what we want to do is when we want to get all the sales orders for a customer, this is going to be the query we're going to use. Select star from C, where C.customer ID equals customer A, and C.type equals sales order. Okay, so let's see what that looks like here. I'm going to query sales orders by customer ID. And let's go out of here. And I'm going to query sales orders by customer ID. Here I've got my customer container reference. Here's my customer ID. This is the same customer from before, by the way. Here's my query that I showed you earlier. Here's my query definition, my parameter, my partition key, and then I'm going to iterate through that and show all the sales orders for that customer here. So that's operation F. And here we go. I've got one order here. This is I don't know what this is. It looks like a bike frame. It's expensive. And then we've got another sales order here. So, yep, I got two orders for this customer in here. And you can see, okay. So let's go, whoops. Let's go back to slides. Okay, finally, we're going to look at the last request we need to serve here, and that is we want to query top 10 customers based upon the number of sales orders they've had. So this requires you to count the number of sales orders for each customer and then sort these counts in descending order and then return the first 10 of those. Now, even though customers and sales orders sit in the same container, this is not actually something I can do with Cosmos DB's query language. So once again, the solution here is we're going to denormalize, and I'm going to put a new property in my customer document that's going to include the count of sales orders within my customer entity. So what we want to achieve is that each time I had a new sales order, I'm going to update my customer document within here. Now, the nice thing is that because these things sit within the same logical partition, I can actually use transactions to do this operation and do them in a very transactional or ACID type manner. And that may be unusual because I said we don't support kind of relational constructs, but Cosmos DB does support transactions for data that sits within the same logical partition. And the reason we can do this is because it sits in the same logical partition, it sits on the same physical partition. And we can do these things when the data sits on the same physical piece of compute. Now, we can do this in two ways. There's stored procedures, which you can write using JavaScript, using our API there. You can also use a new feature, a relatively new feature in our SDKs called Transactional Batch. Okay, so once I do that, now I can serve that query or serve that operation with this query. Select top 10 from C, where C.type equals customer, and then order by C.sales order count in descending order there. Okay, so in this demo, I'm going to show you a bunch of stuff. I'm going to create a new sales order, and I'm going to update the order sales order total for the customer document, and I'm going to do that in a transaction using transactional batch, and then I'll show you how to query for our top 10 customers. Okay, so query customer and sales orders by customer ID. Sorry, I am going to run that, but I want to show you this one here. So create a new order and update customer order total. So I've got a reference to my customer container here. Here's the customer ID. Again, same customer as always. I'm going to read that customer first, put that, deserialize that into a customer object here. I'm going to increment sales order count property. Just sales order count plus plus. I'm going to then create a new sales order object here. So I've got order ID, sales order as my type, customer ID, order date, no ship date because it hasn't shipped yet. And then a couple of items in the cart, so a mountain frame and some socks. And then I'm going to call this function create transactional batch that sits on my container, customer container object here. And I'm going to pass in the partition key. And then I'm going to pass in the operations that I want to run in that batch, in that transaction. I'm going to create an item first, that's creating my sales order, and then I'm going to call replace item, which is the update, on my customer object there, and pass it the customer ID within there. And then I'll call execute async, and then I'll check to see was this successful or not. Okay, so let's run this. So we're going to query for the customer and all orders. Let's run that one first. Whoops, that's not what I want. Create a problem here. Okay, good. Okay, so here's my customer. Oh, you know what I want to show you? I had one more thing. I do want to show you this. Query by customers, delivers a customer ID. So let me show you this code because this is a little bit different. When I'm mixing entities inside a container, I can no longer deserialize these directly into classes, right? Because I have a mix of entities, and I don't. If I try to do that, I'm going to end up with a problem here. So what I need to do is when I define my get item query iterator, I need to do that, deserialize that against a dynamic object here, and then as I iterate through that, I need to inspect the type property, right? So because I'm getting both the customer object and the sales orders, I'm going to iterate through these and then figure out, okay, is this a customer object? And then if it is, okay, great. Now I'm going to just call deserialize object, and then deserialize it into my customer object here. And then the same with the sales order, right? And because I've got multiple sales orders in here, I'm going to add those to a list object that's typed as sales order within there, okay? So I just wanted to show you that quickly because here's the code for that. I've got the customer ID within here. Excuse me, where are you? Here we go. I've got customer ID here, customer, their address and everything. And then the sales order count in here. So I've got two sales orders for this customer, and then both of their orders, right? So here's the first one, and then here's the second one. Okay. All right, now I'm going to create a new order, and then I'm going to update the total for that customer. So that's operation H. That's the transactional batch. within there. Now, let me run that query again. And you can see I've got, here's my customer, Destiny Peterson again, and sales order count of 3 within there. And then here's the first one that I had. Here's the second one that's been in there, right? It's 2013, so it's old. And then here's the one from today, right? So the mountain frame and the socks within there, right? Now, one other thing I want to show you is transaction batch. That works great for adding stuff, but I can also use it to delete as well, right? So it's the same code again, functionally, except I'm going to call sales order count minus minus. And then I'm going to use transactional batch again. I'm going to delete the order out of that container, and then call update or replace item on the customer object to decrement the sales order count. So if I delete that order in here, delete successfully, and then query G. So I've only got those 2 orders, and then look at sales order count is back to 2 within here. Okay, so there we go, using transactions to update different documents, or to add a document and update a document, all in the same batch there, right? So this is exactly what you need for your e-commerce workload. Okay. All right, moving on. Okay, so we're nearly done remodeling our database, and we've created the following containers. So I've got a customer container partitioned by customer ID, and that's got my customer and sales order entities. I've got a product container that's partitioned by category ID, and that contains all my product entities. And then I have a product tag container with partition key of type, and then a product category container partitioned by type. Now, as you may have already guessed, I can make one more operation or one more optimization here, and I can store product category and product type in the same container, right? Remember, they share the same partition key, right? And this is why I made this, or did that weird modeling thing where I created a type property and made them a single partition query. It wasn't for the performance. It's because the optimization here is one around storage, right? Now I can put all this data in a single container that's got 400 RU throughput rather than 2 containers that have 400 RU throughput, which is the minimum amount of throughput you can have on a container, and store them in there. And then when I want to get them, I just use that type property I can distinguish between what I'm using in there. The other thing as well is that I only need one instance of Azure function to monitor it for any changes I want to make in there. So this is really a best practice when I've got a lot of master data or reference data within there. Just store it all in the same container, and then just query for it as you need to kind of hydrate your user, your UX, or your application, or whatever it is you're using it for. Okay, so here's our final design. We've gone from 9 tables in our relational model to just 3 containers. And all of these are perfectly optimized to scale to essentially infinite size. It doesn't matter. These are all perfectly optimized to be able to grow, and they're going to have good. You're going to have good performance and good scale, and do so efficiently as well. Okay, so key takeaways. I hope you understand the importance of understanding access patterns for this. Understand that partitioning is absolutely critical to designing for scale. This is how you achieve that infinite scale, is understanding the partitioning and understanding that the access patterns for your data is what is so critical to getting that right. Using things like embedding data and denormalizing and pre-aggregating. These are all things that are fine in a NoSQL database. You really want to optimize around the request for your applications rather than storage, right? Think about this. When relational databases were designed or came to light 50 years ago, right, 1970, storage was really expensive. Today, storage is cheap. I've got a phone here with like a terabyte of storage on it that just cost me a few $100. The thing that's expensive today is compute relative to that storage. So duplicating data, denormalizing, all of that stuff, perfectly fine. You want to optimize around the request, around the compute for that. And then you can achieve a lot of these things using just different techniques and different methodologies, whether you're using change feed or using our stored procs or transactional batch to achieve all of these things. Cosmos DB has the tools necessary to be able to do these types of things. Here's some links for going further. Everything I just showed you is in GitHub, github.com/AzureCosmosDB/CosmosWorks. Got a link to my deck in there. Got a link to everything. You can got an ARM template. You can set this up and deploy it. Scripts you can run that'll set everything up, load your data. One thing I'll keep in mind is that each one of these databases, it's provisioned at the database level. I tried to keep it as efficient as possible, but it's 4,000 RU in auto scale. If you go and run this thing, don't leave it up because it's going to cost you like $100 US a month to keep it there. So there's menus in there that'll load the data and then unload it all. So when you're not using it, just run that option and it'll delete everything, and then you can keep the account up and that'll run that. You can keep that for free. YouTube, we got lots of cool videos. I have a podcast that I run most every week, aka ms/CosmosDB Live TV. Come and check it out live, or watch lots of episodes on demand. I have a global user group that we started, meetup.com/Azure CosmosDB Global User Group. Feel free to come check that out. We run monthly meetups. I think we're done to the end of the year, but we'll pick up again in January. That's it. I think I'm right on time for an hour, and I'll take any questions that you may have. I think I've got I've got some questions here. How would you handle history, like customer changing address? Well, I don't know why I would keep the old customer's address, but I could use change feed on that. And so if a customer updated something, I could write that to another container and keep it in there. If I didn't want to keep that hot, I could probably use change feed and just write it to a blob storage or something like that if I didn't need to keep it in there. You could also model the data such that I can have active addresses and inactive addresses. So I could have addresses that is just simply an array inside there, and then I would show the ones that I want. What's the difference between Cosmos and Dynamodb? I'm not going to answer that question. I don't work for Dynamo, and I don't do product comparisons. How do you migrate a customer if they buy enough to go past 2 megabytes per customer? So I would use change feed and then design that such as it iterates through every document in there. I'm going to basically either shred that document, or I'm going to do something where I need to put that data and split it up and put it into different rows so I can get that customer underneath 2 megabytes. 2 megabytes is a lot of data for a customer. So there'd have to be, I would definitely want to look at the model within there, make sure that that's correct. Okay, that's all I've got for questions. I'll just leave that up there. Don't think there's any more top questions. Okay, that's it. I'll hang out here for a few minutes. Otherwise, thank you very much for joining. I wish I could have been there in person. I just found out about a week and a half ago how challenging it was for people in gray countries, as they call them, to get into Norway. We'll try again next year. Hopefully things will get a little better. But thank you very much for joining, and enjoy the rest of your event, and enjoy your evening. Thank you.